going to start today by actually talking about something that's really physics. So far we've been talking not so much about physics, but just getting background information. So we're going to start by focusing on kinematics, which is how things move. Not why they move, that's dynamics. Kinematics is just how they move. And today we'll pretty much be introducing just a few of the kinematic variables. So I like this graphic because it actually, if you look at it, you have nice definitions for all the things that we're going to talk about in today's lecture with somebody who has more artistic skill than I will ever have. So the first thing on my list here is position. Now, some of these, you got to bear with me. They're really, really simple. Like, who gets confused on what position means, right? But position, of course, is measuring the actual location something has. So I'm just going to write location here just so we have a word to go with it. Distance is more interesting. Oh, and the variable we use. We use the variable x to indicate the position of something. That's just a standard. You will find people who use something different. Sometimes you use an r, but x is the general variable we use for keeping track of where something is. Now, distance is the change in position. In physics, we use a symbol for change that you may or may not know, and that is the capital Greek delta. So delta x means change in position. Knowing that delta means change in is great, but it's a little better if you know what we mean when we say change in. Change in, delta, is always going to be the final minus the initial. So anytime you see delta x, that's just a shorthand way of writing x final minus x initial. The final position minus the initial position. And so that's a pretty simple nomenclature. But it might be new. I would imagine it's new to a number of people. Then we have displacement. And this is where we get to a word that may not be as familiar for the physics meaning here. Now, we probably all are somewhat familiar with displacement, like when I jump into the swimming pool, I displace a bunch of water. Right? We can talk about Archimedes, and we will later on. But when we're talking about kinematics, displacement is change in, I'm going to put position again, and you're going to say, well, that's the same as distance. I mean, unless you're not paying attention, you'll say that's the same as distance. So how is that different than the change in distance? What's different in the second line that I wrote? It has directions. It has a little arrow over the x, which means that it's a vector. So displacement is the change in the initial position and final position vectors. So it's going to be a vector quantity. It's going to have direction. And it's not always as simple as you might think. If I walk from here to my house, I might cover 3/4 of a mile. But if I look at a map and I look at the difference between the starting and ending positions, that would be only about 2/3 of a mile, right? There's a little difference. Why? Well, I don't walk a straight line to my house. I have to zigzag a little. And so the displacement is just the distance between those two endpoints, whereas the distance is actually, I have to break it down to each piece. I walk this far in this direction, so I have that distance, plus this far in this direction, so I add that distance to get the total distance. Or a simple example that I use that's pretty clear. Let's say that I'm, at the gym and ever since my pulmonary emboli, I really can't jog, but I walk around the track. And so I start in one place and I just cruise around that track. At the gym I go to, believe it or not, it only takes 12 laps to get a mile in. It's a really large track. By sarcasm. So I've walked around, I came back to where I started. If I'm at the gym I go to, that's 1/12 of a mile is the distance I covered. And so this delta x without a vector sign would be 1/12 of a mile. But what's the displacement, the distance between my starting position and my ending position? 0. And so the displacement is wildly different from the distance I travel. So that's the difference in these two. One's a vector, and it's just the difference between the starting location and the ending location. The other one's a scalar, and it's going to be the amount of ground that was covered. Then we get to speed and velocity. Speed, well, we all know. We drive our cars going 85 miles an hour down. What is the speed limit there in Texas? Don't you guys have highways with 85 miles an hour? Yes, okay. We should move to Texas just so we can drive at a reasonable rate of speed without having to worry about getting a ticket. So speed is, physics words, rate of change in position. Okay, those words are meaningful, kinda. The rate of change means how much change per time. It's how quickly the change is occurring. And of course, in physics, we really like to use equations a lot because they say many more things without having obscure words get in the way. But you have to learn what they mean. So the equation for speed, V, is equal to delta x over delta t. Now we have it right here on the screen. Everybody should know the answer, but just to make sure we reiterate it so we don't have confusion, if I were to write this in a longhand form of equation, instead of using the delta, what would I have in the numerator here? Okay, x final minus x initial. And what would I have in the denominator? Time final minus time initial. So that's the speed. Now I'm going to introduce right here an important concept, instantaneous versus average. The average speed, you'll just take the total distance covered divided by the total time it took. The instantaneous speed is trying to squeeze that down to an instant in time. Now, there are highfalutin physics theorists that will say, but there is no such thing as an instant. And I don't care as far as this goes. Instantaneous means we're squeezing the time down to a really, really small amount. As far as you and I are concerned, if I squeeze that time down to like, how much distance did I travel in a millionth of a second? I think we'd all be satisfied to say that's close enough to instantaneous. And so to find the instantaneous speed, you take that same equation. This equation that I wrote, quite technically, is V average. Sometimes a book will put a line over it without an arrow to indicate average. I don't do that simply because it's too close to the vector sign. So I just put a subscript average. The average is that change in position divided by change in time. And if you make the change in time really, really small, you're approaching the instantaneous speed. Now, when you're driving your car on the freeway, which one of those is it? Get back here in case somebody over there is going to answer. Which one of those is the car telling you? Is it telling you your average speed or the instantaneous speed? It's pretty close to instantaneous, right? I mean, it's not perfectly instantaneous because, can't really get down, but it's an instantaneous speed. Velocity. We've talked about the difference in speed and velocity. Velocity is the rate of change in displacement. Or in equation form. So your average velocity equation is just like your average speed equation, except for you're using displacement. So if I did my one lap, my average speed might be, 4 miles an hour. My average velocity, 0. So we understand all of these terms? Any questions about those terms at all? Now we will introduce acceleration, our next lecture on Friday. Those are the only ones we're going to use, and we're going to just look a little bit today at how to work with these equations. So first, now as you should have seen from the message I sent out, the bookstore is not yet online with selling the licenses for ResponseWare and whatnot. And so I'm still going to be using the clicker questions this week, but they won't count as part of your participation grade. So this is like practice for you to go through and have practice trying to answer, answering. So just go ahead and I'll give it. You got a question, Paris?
You have the channel?
Okay, yes. The channel, and I'll write it here so both people can see it. Actually, in this classroom, it's the only one the channel makes sense. The channel is 33, and the session ID is capital W, lowercase EBB, and then all caps PHYS. No space in there. It's just 8 letters. Somebody from Southwestern said that they were having a hard time getting connected to that session ID. It said it didn't exist.
Yeah.
You're having that same problem?
Yeah.
Debbie, can you figure it out?
Right now, did you sign in when you
Yeah.
started training?
Yeah.
You added this session?
Yeah.
Response form? So it didn't work for anyone? It worked last time, but not this time? So capital W,
Yeah.
EBB, capital P, H, all of the rest.
I can't see the screen that has it anymore. I'm not sure why. Maybe Michael did something to me.
Go here. Oh, so we do have 17 people have already responded. So
Yeah,
they've
well,
already-
17 responded, but if you look at them, like on this, they're all clickers. These are all clickers.
Oh, okay. So go ahead and go back to turning
Well,
to
can't
your
actually.
that well there, and you want to exit from here, and you have to. Then it will say, yeah, just close it and go back. You
sorry, everybody. We're trying to figure out why it's not working.
may-
So
go
close
ahead
the
and
presentation.
Don't say that. And then just go to this cloud. Just start your desktop.
Go ahead, you do it. Okay, while she's working on that, I'm just going to move forward. We'll not worry about the clicker. She'll try to figure out what went wrong there.
So you started there,
Yeah,
but then did
That's-
you?
how you started. you can't have the clickers running without it. Okay, so, well, actually, since we didn't get things really working right there, and she's working on it, this was a poll. How many people have done it? I hope everybody
Did you
has
do
created
this?
their expertise. Yeah, that's how you get the web physics thing to start.
Okay.
Sorry, I get frustrated with
Technology doesn't work, and it's so funny because we're both tech people, but when we're teaching, it's different.
web phys and hit start session. Okay, so position conventions. When we're measuring position, we have, like I said, the standard of using X for position. If it's one-dimensional. If it's more than one-dimensional, well, I'll have a second slide that shows the standards for more than one dimension. But if there's only one dimension, we generally consider X to be the direction of motion. And by convention, going to the right is positive or going up is positive. Going to the left is negative, going down is negative. So in this picture, we have this professor who goes from an initial position of 1.5 meters. Now notice that has an X sub 0. What does the sub 0 mean? Well, it means initial. So she started at an initial position of 1.5 meters. She moved to a final position of 3.5 meters. And thus, her change in position was 2 meters. What about her displacement? You need one more piece for the displacement besides just 2 meters. 2 meters to the right. And if there's only one dimension, we will just say positive and negative instead of saying to the right or to the left. So if it's only one dimension, that works for us. If it's more than one dimension, we have to be more careful. So Jordan's answer of positive is going to work if it's one dimension. Now, a more complicated situation, the dude here is on an airplane. Now, we're going to have the airplane picture a few times. Obviously, if you've looked at the textbook, which you should have all done for your concept codes, you've seen the picture, and you'll see the ones coming up. This man's in the airplane. The airplane, of course, is moving as you're looking at it to your right. I almost said to your left because I'm looking at you. The airplane's moving to your right. The man's walking to the rear airplane. Being real logical here, if you're standing on Earth and you were trying to track that man on GPS, what direction would you see him going? You'd see him going to the right because the airplane's going a lot faster to the right than he's going to the left. This picture is used for the simple reason of helping us to realize that when we're making measurements of position, we're doing it with respect to a specific reference frame. And so all these measurements are going to be made specific to the reference frame of being in the airplane. So the fact that it's an airplane is completely unimportant to all the pictures that have the airplane. We're only looking at his motion with respect to the airplane. So in this airplane, he walked backward 4 meters. And the only reason we have this here is to pay attention to the line got longer because he went a longer distance. When we're using lines to represent motion, we need to make sure that our lines actually have a length that's representative of the magnitude of the motion. So if you're adding distances proportional to the distance, because students often ask this, just to make sure, magnitude simply means the size. So here you went back. Now that was simple. I put this in between, I rearranged them, and apparently I didn't rearrange them the way I wanted. Remember I said we used for convention X for horizontal, and we talked about others if there were 2 dimensions. It won't just X for anything. But if there are 2 dimensions, X for horizontal, Y for vertical. Don't have a picture here, but if it's 3 dimensions, the convention is even more, we switch it. If we have 3 dimensions, X and Y are the 2 horizontal directions, and Z is the vertical direction. These conventions can be a little confusing because, Y was vertical. If it's 1 dimension, X will be vertical. If it's 2 dimensions, Y will be vertical. If it's 3 dimensions, Z will be vertical. It's only a convention. It doesn't change the solution. So when you're doing work, you don't have to follow the convention. But when you're reading the textbook, you need to understand the convention so you can read the textbook and understand what they're doing and why they have the labels. Whenever you're drawing a diagram that has more than one direction, make sure you draw something like this to indicate what you are using for your different directions. Right? Even if you're using the standard convention like this, draw it out so it's clear. Yeah, this person's following the standard convention. Rather than, well, they went this distance in the X direction, whatever the world that might be. Then they went this distance in the Y direction, which I assume is perpendicular. That's another thing. Your directions need to be perpendicular. We need our coordinate system to have perpendicular dimensions so that changing in one direction makes no difference in the other. If they weren't perpendicular, like if you tried to define X like this and Y like this on a flat surface, not trying to make a 3-dimensional surface here, and you have something that moves from this position to this position, well, that's parallel to the x-axis, right? But if you were to try to lay out, coordinates, you could say, well, it actually moved some in the y direction because the y direction has a certain amount that is going to be going that same direction. So you can say, it moved like way out here, They have to be perpendicular or you can't actually identify 2-dimensional or 3-dimensional motion. So it's important that your dimensions are perpendicular and that you label them. The conventions are positive to the right, positive up. Now, adding vectors. I'm like halfway through my slides. I might finish early. There's a chance. When I was like in 1st or 2nd grade, I am the only idiot in my family who went to 1st grade, believe it or not. Everybody else looks down on me as being the idiot that went to 1st grade. Everybody else just started in 2nd grade. But when I was a kid and went to 1st grade, our teachers taught us to add like any good teacher would. And the way we did it was a number line. Is that how you guys learned to add? It's a number line? Glad to see some people who learned the same way. And so if my teacher gave me a problem that said like 2 plus 3, what I had to do was have my little horizontal line, and here's 0, 1, 2, 3. I know 2 plus 3 is 5 just off the top of my head, so I stopped at 5. So then I draw an arrow that goes from 0 to 2, and then at the end of that arrow, I put another arrow that goes from there 1, 2, 3 more. And then my teacher, because she had no faith in me, told me that I had to sit here and count how far it was from here to here. And that's how I got 5, right? When you're in college, that seems pretty ridiculous. But, when you're 6 or 7 or whatever, for some students, it was hard. Well, that's exactly how we add vectors. That is the way we do vector math. When you have vectors, the vectors aren't necessarily going to be all in the same direction, but you still do the same thing. You draw the first one starting at your origin, the beginning point, and then you draw the second one at the end of the first one. So let's just do a little example. I should have preloaded a blank page in here. So let's just do an example. Let's say that I have 2 vectors that I'm going to add. So I'm going to have vector A is equal to 3 in the x direction. So I'm going to put an x with a little, we call it in math, a hat. That x hat means that it's going in the x direction and the x hat has a magnitude of 1. It's called a unit vector. Unit because it has a magnitude of 1, and since it's x, it's in the x direction. My x's and y's don't always appear distinctly different. Okay, so that's my first vector. My second vector, b is equal to 3y hat. What would y hat mean? It's in the y direction with a magnitude of 1. Now, if these are values, and we're in a physics class, we pretty much need to have units, right? When you were in grade school, there were no units involved. In physics, there's going to be units. But for the sake of this, I'm not going to worry about units. Just magnitudes of 3 with, it could be newtons, it could be meters. It's just adding vectors. So now if I want to add these, I will make an XY coordinate system. And I will be so good as to label this the X, oops, I'm still on the X direction, and I'll label this the Y direction, put arrows on the ends of them to say that's going positive. And then I'm going to add them using the same method that I learned in grade school. So, yes, go ahead.
So why is positive and negative like from left to right as opposed to something like initial outward?
Well, left to right is just a convention. And it's not positive outward because going to your left is going the opposite direction is going to the right. We can't use the same, can't say it's positive going both directions.
Sure.
And so that's why it has to be only one of those is positive. And of course, a negative value is just a opposite of a positive value, so it's going to mean opposite direction.
Yeah, okay.
Okay, so drawing these out, I don't have sizes marked, so I'll quickly put, and of course, I know I'm only going to 3 on each axis. So I draw my first vector going 3 in the positive x direction. And then my second vector has to start at the end of the first vector. So my second vector, I only have a red arrow preset, so that's the reason. So my second vector goes 3 up. How do I know where to stop? Well, I tried to stop where that would come across. So I went 3 over and 3 up. And then the question is, what's the answer if I add these two together? I have my B vector drawn here. I have my A vector drawn here. How do I find A plus B vector? Go ahead. Jordan?
Would it possibly be the hypotenuse of the right triangle?
Okay, in this case, yes, the hypotenuse of this right triangle. You draw your resultant. The resultant is the word we use for the result when you add vectors. From where I started, so from my origin, to where the last one ended. So it's going to go like, okay. You can see that I am not the perfect artist. That's my resultant. So the blue line here is vector A plus vector B. Okay, now I've got this drawn out. I know one side is 3. I know the other side is 3. This was simple. Most people probably can just yell out the answers. How do I find the length of that resultant? I'll use the Pythagorean theorem. So Pythagorean theorem says what do those two lines mean? The two vertical lines?
Value.
It's the absolute value. In physics class, we'll say the magnitude, the size of it. So the magnitude of A plus B is going to be found by taking the square root of the horizontal portion, which in this case was 3 quantity squared, plus the vertical portion, this 3 quantity squared. And so that's going to be, or 3 squared, 9. 9 plus 9 is 18, the square root of 18. Or for people that want to do it a different way, 3 times the square root of 2 is what you get. That'd be 4.2. So my magnitude is 4.2. Now, you can check on the calculator because I may not be right. I did it in my head. I didn't calculate it. So that's how you find the magnitude. So we're going to have to use the Pythagorean theorem here when we're adding vectors. What about its direction? Well, it's not just positive x, and it's not just positive y. So what's it going to be? What we do, and there are different ways of writing this. One way of writing the answer is actually the component way. I could say a plus b is equal to 3 in the x direction plus 3 in the y direction. That's writing out in components. That was simple. I just took all the x's and add them together. So my first one was only an x, so I took 3 in the x direction plus the second one, 0 in the x direction. 3 plus 0 was 3. The y directions, 0 plus 3 was 3. So that's one way of writing the answer. The other one is to find an angle. And so, once again, by convention, we find the counterclockwise angle going from the horizontal axis. You can choose other axes, you can choose other directions, but make sure you specify where your reference is and which direction your angle went. So if I'm going to find my angle this way, traditionally we use the Greek letter theta to represent the angle. How do I find that angle? Tangent. The standard way to do this is using tangent. Now, anyone could have said sine, anyone could have said cosine, because we found the magnitudes of all 3 sides of a right triangle. And if it's a right triangle, we can use those with reckless abandon. But it's best to use tangent because I knew the x and the y. I didn't have any round-off errors there. Now, while I'm talking about round-off errors, it's important to talk about something with the homework site. In this class, we talk about significant digits and keeping track of them. And, if you have 2 significant digits in your answer and you put 7 digits in it, you just put 5 meaningless digits, and that's going to cost you points on an exam. Well, the homework site does not obey. The homework site, for every problem, it does not matter. They will calculate out to 4 digits. Doesn't matter how many significant digits there are. And then they have a plus or minus like 1% or 2% that they use. So when you're doing homework problems, just treat every answer as if it has 4 significant digits. When you're doing calculations, you never apply significant digit rules until you get to the final answer. The reason you don't apply them early is because even though you had insignificant digits, you're still throwing away information if you apply your significant digits rules before the final answer. So always keep all of the digits in your calculation. That is, just do it on your calculator and keep them all. Or if you want to be a nerd like me, I do all of your homework problems using spreadsheets. Keep all of your digits to the end and then apply your significant digits. But for homework, just put in 4 significant digits. It doesn't matter if they don't honor significant digit rules. Because it's really frustrating to me. I want students to know significant digits and to follow the rules, and homework site doesn't. Got a question, Mr. Meckel?
It's total or after the decimal?
For total. And of course, I only wrote 2 here. When you have a number like 3, if it's a cardinal number, it's infinite number of significant digits. Like if there are 3 people in the room, that's an infinite number of significant digits. There's not 3.1725, and I only knew to one digit. So there's a few other things. Pi, by the way, has an infinite number of digits, and they're known out to far more than we'll ever care to know. So if you use like your calculator, it's going to have 15 or 16 digits in pi. So that is not going to be a limiting factor. You shouldn't just put 3.14 and say, I only have 3 significant digits in pi. Okay, back to this. So using tangent. Now on the exams, you're going to have every equation you need. And I include the equations for trigonometric functions. The reason for this is physics class is about thinking and analyzing things and being able to solve problems, not about memorizing stuff, right? We could sit down and memorize equations. A lot of people do. For the MCAT, I think you actually do have to memorize some equations. But as physicists, we don't care. We just want people to be able to use the equations. So you'll be given, sine of theta is equal to opposite over hypotenuse. Cosine of theta is equal to adjacent over hypotenuse. Tangent of theta is equal to opposite over adjacent is equal to sine theta over cosine theta. And of course, you'll be getting the Pythagorean theorem that says hypotenuse squared is equal to opposite squared plus adjacent squared. So you'll be given those. You'll have to be able to use them. Now, I don't know, funny in my education, when I was in high school, we just memorized these the way I wrote them. And then when I got to being a teacher, I found out other people learned nifty little mnemonics to help them remember. Like some old hippie came a-hopping through our alley. Yeah? No? Or there's, the great Sokatoa. But I will just be giving these to you. One caveat that you need to understand. These equations are true for only one type of triangle. It has to be a right triangle. In fact, the hypotenuse, I believe, is only defined for a right triangle. The hypotenuse is the side opposite to the 90-degree angle. So if it's not a right triangle, you can't use these. There are other laws you can use. You can use the law of sines, the law of cosines. So you have things like C over sine C equals B over sine B equals A over sine A. Anybody seen that? That's the law of sines, and that works for any triangle. I could have sworn I had a triangle tool here, but I guess not. Any triangle that you can make, if you define angles capital A, capital B, capital C, then the side opposite each angle is the side with the lowercase letter to match. And so for that triangle, this law of sines is true, and that doesn't have to be a right triangle. You'll find this useful in some problems. And the law of cosines so far it looks just like the Pythagorean theorem. C squared equals A squared plus B squared minus 2AB cosine of the angle C. That works for any triangle, not just for right triangles. Now, if C is a 90-degree angle, what is cosine 90 degrees? Cosine 90 degrees is 0. So this equation is exactly that equation. It's just the Pythagorean theorem is a special case of the law of cosines. So those are the trigonometric equations. That's the entirety of trigonometry until we get to optics. Right? That's everything we need to know about trigonometry is just on these things right here. And so we're going to use these to find that angle. I spent a lot of time. Now we need to get to the angle because I'm behind time instead of ahead of time like I was. So for my simple situation, I said that it would be best to use the tangent equation because we didn't have to calculate the opposite or adjacent with any, losing significant digits. So I am just going to take my triangle up here and say tangent of theta is equal to the opposite side from theta is going to be over here, 3 vertical. The adjacent side is 3 horizontal. And so tangent of theta is 1. Well, if I know tangent of theta is 1, I know a lot of you know the answer already. But you can just take your calculator, and your calculator has a function, arctangent or inverse tangent. It's an inverse function, so I'm going to put arctangent or inverse tangent on both sides. So I'll write it this way. There's the left side. There's the right side. Arctangent of tangent, they're inverse functions. That means that they do the opposite thing. And the answer you get is just going to be the angle. So the left side of this is just going to be my angle theta. That's a wonderful, beautiful theta. So theta will be the arctangent of 1. Now you put that in your calculator. One more thing to pay attention to. What units is your angle going to be in on your calculator? It could be radians or it could be degrees. Now, I like to say that there's only one correct angle, and that is the unitless one. Radians are technically unitless. There's no angle to a radian. We write down radian to tell everybody we measured this angle in the unitless angle. And so when you're doing equations and you have angles in radians, the radians will sometimes just disappear because they really aren't units. Degrees means that we use a conversion factor. So everybody knows 360 degrees in a circle. Not as many people know why are the 360 degrees in a circle. Gonna look and see if anyone in Southwest knows. Nope. Okay. Ancient astronomers knew that there were roughly 360 days in a year, right? 365.2422 days in a year. And they said, that 365.2, well, they didn't know 0.2422. They knew it wasn't 365, and they knew it wasn't 366. It was somewhere in between. They said, that's really close to 360, and 360 is a really, really cool number. It's really cool because 360 is evenly divisible by 1, 2, 3, 4, 5, 6, got to skip 7, 8, 9, 10, got to skip 11, and 12. So it's evenly divisible by all but 2 of the numbers between 1 and 12. And they said there must be something really magical about this number. It must be really powerful. And so they said, let us approximate that the angle that the sun moves from noon to noon compared to other stars in each day is 1 degree. That is 360 degrees for it to do a complete circle and come back to where it started. And so that's where we get 360 degrees in a circle. It's an approximation on 365.2422, but nobody would want to have 365.2422 degrees in their circle. And it's really easy to do math if you go down to 360. So how many radians are in a circle? 2 pi. Remember, circumference is 2 pi times the radius. Pi comes from that. So the conversion factor is 2 pi radians is equal to 360 degrees. So when you do it, make sure you pay attention to what your calculator says for the units. And if it says what's the angle in radians, make sure you do it in radians. If it says what's the angle in degrees, make sure you do it in degrees. So if you do this calculation, this is a rather trivial calculation, and it comes out to be theta is equal to 45 degrees. And so the second way of writing my answer would be, did anybody calculate to see what this number really is? Too much faith. I will write 4.2, but correct me if I'm wrong, okay? At 45 degrees, but I can't just put at 45 degrees because I need to give my reference point and the direction. So the direction it went was toward the y coordinate. So I'm going to put toward the y coordinate of or from the x coordinate. That completely specifies the direction. It's 45 degrees from the y going toward the, or from the x. Yeah, it's going toward the y from the x is the way you write it. So either one of these is a correct answer, and you'll have problems that ask for it both ways. Question?
You said the first way, the 3 hat x plus 3 y hat is a component. What's the other way?
It's magnitude and direction is the, or magnitude and angle, I guess. So we're going to have to work through these. Now, I feel bad at this point that I chose such a simple set of numbers, 3 and 3. You know, I could have done something more complicated. I'll do very quickly without having to do all the explanations. A more difficult problem here. Let's say I have A is equal to 2x minus 3y and B is equal to minus 4x plus 1y. Now, if I'm going to add this up, I can do the components without drawing a picture. I can do the components just by, as good old Mrs. Bird taught me in high school, apples add with apples, oranges add with oranges, or in this case, x's add together and y's add together. So I'll just take my x's. I had a 2 and a minus 4. 2 plus minus 4, everybody here knows is minus 2. It would be insulting to suggest that you didn't. Oh my goodness, I forgot to put the hats, and those are very important. Otherwise, it would be variables instead of directions. So minus 2x plus minus 3 plus 1 is minus 2. That was still a bad choice. Let's change the numbers on the fly. Let's just make that a minus sign. Minus 3 minus 1 is minus 4. I don't know how I choose random numbers and still end up with trivial answers. Okay, so we could do that right off the bat without drawing a picture. Now that I've done it like that, I can draw my triangle. I can draw my triangle, even though it's not going to have vectors A and B, I can still make the right triangle because I know how much it goes in the x direction, how much it goes in the y direction. So looking at this, and I'm not even going to draw the coordinate system, how much, well, I will draw this much. X goes that way, y goes that way. How much does this go in the horizontal direction, in the x direction? -2, which means that it goes which direction, left or right? Left. So I'm going to have going left a distance of 2, and then the vertical direction, how much distance and which direction? Down and 4. So there it goes down 4. So my resultant goes, where's my resultant go from and to? From where, Keela? Where do I start for my resultant? Okay, the origin, where I started here. And where does it end? The end of the second one. So there's my resultant. And if I want to find the magnitude, I will have the magnitude of this, and I'm just going to call this C. So the magnitude of C is equal to square root of 2 squared plus 4 squared, which of course is square root of 20, or for those who care, that would be 2 times square root of 3. 3.4-ish? 4 point what? Really? Okay. That's a failure on my part. 4.7? 4, okay, thank you. Now, in this case, I had 2 cardinal numbers. I, in theory, have infinite numbers, infinite digits, so I'm just going to stop at that. So magnitude there, 4.47. Yeah, it has to be more than 4. What was I thinking? One side's 4. Notice these 2 sides here were not the A or the B that I plotted, but it was from doing the breakdown. I could have made my first vector that would have gone over to down 3. That's too far. I could have made my first vector. So this here, drawing the two components, that's my vector A. And then my vector B is going to go back 4 and down 1. So there's my vector B. I could have drawn that way, but it gets me to the same place. I've got the magnitude. I want to find the angle. How do I find that angle? First of all, what are my reference point? What line should I find the angle from? There's two logical choices. Doesn't matter which one you choose. Okay, somebody says, I heard the x-axis. I'm going to do it from the minus x-axis just because that one is within 90 degrees of it. And so if I'm going to go from the x-axis, it's going to have to be going clockwise or counterclockwise. Wow, I'm really winning. And now I can find this angle using what we did before, jumping straight to the theta is equal to inverse tangent or arctangent of the opposite side over the adjacent side. Always look at your triangle and say which side is opposite to my angle. Because depending on what reference point you use, it's a different side. If you had chosen to make your reference point the minus y-axis, the opposite side would have been a different side. So in this case, my opposite side was 4, the adjacent side was 2, and so I have to do inverse tangent of 2. Inverse tangent of 2, I don't know offhand. It's how much? 63.4 degrees. And so now I can put A plus B is equal to 4.47 at 63.4 degrees. And I was going toward the minus y-axis from the minus x-axis. And so there I've specified my angle very carefully. So that's how we add vectors. Now, given that I only have 3 minutes left, almost rhetorical question. When you were in first grade and you subtracted, what did you do? You did it backward. The one that was negative, you reversed its direction, and then you added the vector that was in the opposite direction. And that's what we do in physics as well. So if I am subtracting vectors, if I do A minus B, I just rewrite this as equals A vector plus parenthesis minus B vector. So minus B vector means I just reverse the direction of the B vector. There's my minus B, and then I add them like I normally would. So still add them tip to tail, but add A plus parenthesis minus B if you're doing a subtraction. Okay, we will not go over this multiple except for one thing. When I was in graduate school, my professor was a funny man. We had some funny teachers, and one of the things he did on tests, I was in charge of grading the exams. And he had a question. They had the coordinate system, and it had vectors going like this. And I kid you not, this thing had 15 vectors on it. They're labeled A, B, C, D, and so on. And he asked, what is the sum of A plus B plus C plus D plus E, and all of it? This was the first question on the exam. Out of a class of around 200 people, there were about 5 people who didn't get past this one question on the first exam of the year. Because they took each one and they said, okay, I've got to break it into components. And I'll add those, each one broken into components, adding them all up. Well, that's a huge number of vectors, breaking each one into components, adding them all up. Took forever. But that was only like 5 students who failed. Everybody else got it. Why did everybody else get it correct? What's the answer? 0. Because when you add vectors, you add them tip to tail. It was shown with them tip to tail, so it was shown a picture for them being added. And then your resultant is the vector that goes from where you started to where you ended. Well, it ended where it started. So the answer was just 0. And he used this to weed out students. If they were thinking at so dogmatically, they figured they're just going to grind through the class and it would be torturous and save them time and energy. Or so I predict that's what he was thinking. Okay, we're out of time, so that's where we stop. That's where we end.
Lab reports, where do we send those in?
Okay, the lab reports are turned in on Moodle. If you go to Moodle, there is a lab one. You click there. It has a box. You can just drag and drop the PDF into it. It's due tomorrow night. The lab guide says tonight, but it's due tomorrow night.
Leave this on.